What if the key to unlocking the full potential of quantum computing lies in particles, once dismissed as garbage? This bold idea is at the heart of a groundbreaking study that could revolutionize the field. Quantum computers promise unprecedented speed, but their Achilles heel has always been reliability. Qubits, the building blocks of quantum computation, are incredibly sensitive, and even minor disturbances can derail calculations mid-process. But here's where it gets exciting. A new approach, leveraging particles called anyons, might just be the game-changer we've been waiting for. Enter topological quantum computing, a strategy that relies on the unique properties of anyons to store and manipulate information. Unlike traditional qubits, anyons are less susceptible to errors because their computational power is tied to their movement around each other, a process called braiding. Imagine weaving a complex pattern with threads. As long as the pattern remains intact, small tugs or shifts won't unravel it. Similarly, braiding anyons creates a robust knot of information that resists common forms of noise. But there's a catch, and this is the part most people miss. Traditional braiding techniques with Ising anyons can only generate Clifford gates, which are insufficient for universal quantum computing. That's where this study takes a daring leap. Researchers have discovered that adding a single, previously overlooked particle type, an alpha-type anyon, within a broader mathematical framework makes braiding alone computationally complete. No need for ancillary measurements or magic states. Controversial interpretation alert. Some might argue that introducing new particle types complicates the hardware requirements, but the authors cleverly sidestep this by treating the alpha-type anyon as stationary, keeping the setup surprisingly simple. This approach not only preserves the elegance of braiding, but also aligns with existing experimental techniques. So, how does this work? The alpha-type anyon acts as a fixed anchor, while Ising anyons move around it, executing gates within a carefully defined computational subspace. This subspace is designed to avoid sectors within definite norms, ensuring unitarity, a critical requirement for reliable quantum operations. The team also identifies specific braids that function as single qubit gates or entangling gates with minimal leakage, a feat that's both precise and practical. Thought-provoking question. Could this be the missing piece in the quantum computing puzzle, or are we underestimating the challenges of implementing such exotic particles in real-world hardware? Looking ahead, the next step is to identify materials that can host these alpha-type anyons, known as neglectons. Fractional quantum Hall states and engineered defects in topological superconductors are promising candidates. Early experiments might focus on detecting spectroscopic signatures or interferometry patterns unique to neglectons, providing a proof of concept without requiring full quantum computation. In the lab, two-dimensional electron systems exhibiting the 5-2 state and topological superconductivity platforms remain the most promising arenas. These systems have long been hailed for their potential to support fault-tolerant operations. The study also offers detailed Hilbert space bookkeeping, giving experimentalists a clear target for controlling excitations and braids in initial tests. Mathematically, the authors urge extending the parameter ranges where their construction guarantees dense single-qubit gates and efficient entangling gates. On the hardware front, advances in superconducting circuits that emulate Ising anyon rules suggest that integrating a stationary, alpha-type defect could become a practical design feature rather than a theoretical curiosity. Published in Nature Communications, this research opens up exciting possibilities. But what do you think? Is this the breakthrough quantum computing needs? Or are there hidden pitfalls we're not yet considering? Share your thoughts in the comments. Let's spark a discussion.